Hello everyone, I hope everybody is fine. We want to talk about a couple of new exponent laws. In junior grades, especially in grade 9, even in grade 8, we learned about exponent laws, many of them. For example, if you have two powers with the same base but different exponents, when you want to multiply them, you write down one of the bases and simply add the exponents, for example. So those laws we already know, but we want to learn about some new laws. And in order to do this, we are going to do a very brief, short investigation. If somebody asks you what is 2 squared, you're going to say, well, 2 squared means 2 times 2, which is equal to 4. So you are absolutely right. It is 4. And 2 raised to the exponent of 3 means we have to multiply 2, which is the base, 3 times by itself. And the number of times that you multiply the base 2 by itself is actually the exponent. So we have 2 raised to the exponent of 3, which is equal to 8, obviously. 2 raised to the exponent of 4 is going to be 2 times 2 times 2 times 2, which is the same as 16. 2 raised to the exponent of 5, obviously 32. 2 to the 6th is 64, needless to say. 2 to the exponent of 7 is 128, and the list goes on and on, just like that. Now, when you look at all these numbers, you may notice some sort of pattern here, and that is if you divide 128 by 2, you get 64, right? And when you divide 64 by 2 again, you get 32. And working backwards again, if you divide 32 by 2, you get 16. So each time, if we divide the number by 2, we get the result that we had in the line above. And this pattern that you may notice keeps going on and on and on. For example, if you ask what is 2 raised to the exponent of 1, it's going to be actually 2, obviously, and that is actually 4 divided by 2. Once again, the pattern is valid. So it makes sense, if we have 2 to the exponent of 0, it makes sense to say that the result will be 2 again divided by 2, which is equal to 1. So we come up with this conclusion that the base 2 raised to the exponent of 0 is actually equal to 1. It makes sense to say so. And instead of the base 2, of course, I could have used base 3. I could have written a list of powers of 3, a list of powers of 4, powers of 5, just like that, or actually any base instead of 2. And the same pattern would still exist. For example, if I had 3 to the exponent of 2 and then 3 to the exponent of 3, this is 9, this is 27. So this time, instead of dividing by 2, I would divide, of course, by 3, I would get 9. And then 3 to the exponent of 1 would be 3 because 9 divided by 3 is equal to 3. So same pattern that we just discovered together is valid for actually any base, 2, 3, 5, 6, whatever number. Generally speaking, we say that any number, any base raised to the exponent of 0 is equal to 1. And that is the exponent law we wanted to learn today, one of the two exponent laws. So if I say, for example, what is 7 to the exponent of 0? The answer is obviously 1. Even if you have a negative number like negative 52 raised to the exponent of 0, it doesn't matter. The answer is 1. Even if you have a fraction such as 3 over 11, again, you raise it to the exponent of 0 is equal to 1. So basically, any number raised to the exponent of 0 is equal to 1. Of course, except 0 itself. Okay, so what happens if we keep continuing the same pattern just to see what happens? We had 6, 5, 4, 3, 2, 1, 0 as the exponent, and now I wonder what would be the result if the exponent was negative 1 actually. Well, the same pattern logically might continue, and I might divide 1 by 2, which I'm going to get 1/2, which is 0.5 as a decimal. And if I keep going, 2 to the exponent of negative 2, I would divide this by 2 again, and I get 1 over 4, which is 1 over 2 squared. And then if I keep continuing, 2 to the exponent of negative 3 would be 1 over 2 to the exponent of positive 3. Because if you divide by 2, that's what you're going to get. This is actually 0.5. This is 0.25. And this is 0.125, which is half of 0.25. So we see that the same pattern continues. It's very interesting pattern here. So we come up with this conclusion when you look at all these different examples. You come up with this conclusion that any number raised to a negative exponent equals to the reciprocal of the same number with positive exponent. Just like 2 to the exponent of negative 3 was actually equal to 1 over 2 to the exponent of positive 3. 1 over 2 is the reciprocal of 2 itself. So we come up with this second exponent law. So if I give you an example, if you have, let's say, 5 to the exponent of negative 4, that is actually equal to the reciprocal of 5, which is 1 over 5, raised to the exponent of positive 4. Or if you have, let's say, 8 to the exponent of negative 1, that will be 1 over 8, which is reciprocal of 8, obviously, to the exponent of 1, which I don't bother writing it down. If you have a fraction, for example, 2/3 raised to the exponent of negative 2, that will be equal to the reciprocal of the fraction, which is 3 over 2, and then raised to the exponent of positive 2. All right, and then, of course, we know the answer is going to be 9 over 4, because you raise the numerator and the denominator both to the exponent of 2. So having said that, if we have a couple of examples here, we can perhaps find the answers. Negative 3 over 4 inside the brackets raised to the exponent of negative 2. That will be actually the reciprocal of negative 3 over 4, which is negative 4 over 3, raised to the exponent of positive 2. Okay? And if you evaluate that, that's going to be negative 4 all squared divided by 3 all squared, which is 16 over 9, needless to say. Here we have 1 over negative 3 raised to the positive exponent of 2, and that is going to be 1 over 9. Here it's going to be 1 over again. We said that's the reciprocal. Same base, negative 4 raised to the exponent of the positive exponent. So that's going to be negative 64. So negative 4 raised to the exponent of 3 is negative 4 times negative 4 times negative 4, which is going to be 16 times negative 4. That is negative 64 in the denominator. So negative 4 inside the brackets, all raised to the exponent of negative 3 equals 1 over negative 64. In other words, same as, of course, negative 1 over 64. Any number, okay, any of these integers raised to the exponent of 0 is equal to 1. It doesn't matter if the base is 7 or 8 or 9. So this is actually 1 minus 1 plus 1, which is equal to 1 final answer. Now this one, the negative sign is outside. So we have 1 over 5 instead of 5 to the exponent of negative 1. And the final answer is negative 1 over 5. Remember that it makes a difference sometimes if the negative sign is inside the brackets or it is not inside the brackets. For example, if you have negative 2 raised to the exponent of, let's say, 2, the answer is positive 4. Because negative 2 times negative 2 is equal to positive 4. It's not a secret that negative times negative is positive. But if this bracket is not there and you only have negative 2 raised to the exponent of 2, we just do 2 squared, which is 4, and we put the negative sign in front, so the answer is not positive 4 anymore. So you have to be very careful about this issue, which is not something new, mind you. To do some other exercises, we have equations that we call them exponential equations. 2 to the exponent of n is equal to 1 over 16. How would you solve for n? What is the value of n such that left side equals right side? In order to do this question, we can say 16 is actually 2 to the exponent of 4. I believe we had it before right there, here. So instead of this, we can write 1 over 2 to the exponent of 4, right? But then using the negative exponent law, we said that any base, any number raised to the exponent of a negative number is equal to the reciprocal of the same base with the positive exponent. So this one, I can rewrite this as 2 to the exponent of negative 4 on the right and equals 2 to the exponent of n on the left side. So you see here we have 2 powers, one on the left, one on the right. And these powers have exactly the same base of 2. So the only case, or the only time that this equality of the two powers with exactly the same base of 2 would hold is when the exponents are perfectly equal. That is, n must equal to -4. Because think about it. If the exponent on the left side is not -4, let's say it's -3, how can you say that 2 to the exponent of -3 equals 2 to the exponent of -4 on the right-hand side? It's impossible. So the only time that this equality would hold is when the exponents are also equal to one another, because the bases of the two powers are exactly the same. Okay, in this next question, we have 4 to the exponent of n equals 64. I think we can write 4 cubed instead of 64 on the right-hand side. And by writing 64 as a powered base of 4, we can see that, again, if the exponents are equal, then the equality would hold. These two powers, both with the same base of 4, would equal to one another only when their exponents are equal to one another. That is, n equals 3. And that is the solution to this simple exponential equation. This one is so easy because I would say n is equal to 0, easily, because we just said that any number, not necessarily only 11, but any number raised to the exponent of 0 is equal to 1. When I say any number, obviously, I'm not saying 0, because 0 to the power of 0 is a meaningless expression, but any non-zero number or fraction or integer, or any other non-zero real number raised to the exponent of 0 is equal to 1. So because the right-hand side is 1, this exponent on the left must have been 0, and it cannot be anything else. If n is equal to 1, on the left side we have 11. If n is equal to 2, we have 121 on the left-hand side. How can I say 121 is equal to 1? So n must be equal to 0 and nothing but 0. This other equation, again, 27 is 3 cubed, right? So this is actually 1 over 3 cubed, okay? And we can write this in the numerator with a negative exponent. So that will be 3 to the exponent of -3 equals n to the exponent of -3. So again, we have two powers, one on the left, one on the right. The exponents are perfectly the same, and the bases must be the same in order for this equality to hold. So we're going to conclude that n must be equal to 3, which is the same base of the power on the right-hand side. Okay? So n is equal to 3 is the solution for this equation. This other equation has n equals 0. The solution for this one was n equals -4. For this one was n equals 3. I think I gave you other examples as well. And these two are the most important formulas we need to learn in this short lecture. We call them exponent laws. It's the continuation of the exponent laws that we have learned in the past junior grades. And I hope this investigative method that we applied was good enough for you to understand why any number raised to the exponent of 0 is equal to 1, and why any number raised to a negative exponent equals to the reciprocal of the same number with the positive exponent n. So I guess now you need to only do some practice questions. There's lots of questions in your textbooks. You can, of course, try them and become better and better at applying the exponent laws. Thank you for your attention.